Welcome everyone to our fourth Scalable Pandas Meetup. We had a bit more of an exciting introduction than I had planned, which was collectively as a community, an open source community trying to debug Peter's sound issues. So I apologize for that. I'm so excited that we're here with Stefan, and I'm really excited to get to chat about Hamilton today. So here's the agenda. So first, we're going to briefly recap Meetup goals and then do some really quick introductions. And then we'll dive into the main thing, which is building data frames with Hamilton. Stefan will present, and then I'll ask some questions, and then we'll have some audience Q&A. I wanted to remind you that this meeting is being recorded. If you have any issues with that, we're planning on putting it on YouTube. Please let me know. You can email me at peter@ponder.io, but it should be okay because we tried to be explicit with the sign up things that was our intention. Okay, so what are these meetups about? So we started these meetups in order to discuss challenges that arise when you have really complex workflows and large data sets, when you're trying to use pandas for those, and we want to talk about solutions to those challenges. So we're here to talk about best practices, examples, and to come together and learn as a community. Who is Ponder? Ponder is the enterprise-ready pandas company, and it's the primary developer of the open source tool Modin, which is a scalable pandas library. Why did Ponder start these meetups? Our goal was to create a community around trying to tackle pandas challenges at scale. We wanted content and learning material to come out of this as well. I'm excited. It feels like more and more there's a growing body of people who are interested in trying to use pandas in really professional ways, and that's exciting to see. How often will these be held? We hold these on the fourth Thursday of the month. Our next one will be, I think it's September 22nd, but anyway, the fourth Thursday in September. And how could I get involved? You can email me at peter@ponder.io for feedback or suggestions. If you'd love to present at one of these, we'd love that. Okay, so I'm excited to get to introduce Stefan. So Stefan's former manager of the, it's funny, it's abbreviated ALG. I'm never sure if it's like algorithms or algorithmic or there's also, anyway, the algorithm development platform team at Stitch Fix, former software engineer at Nextdoor, former data scientist engineer at LinkedIn, has a master's in computer science from Stanford. And he's gonna talk to us today about more about Hamilton. And then also it's fun to see that Elijah Ben-Izzi is here. I've seen Elijah's name on a ton of Hamilton commits as well, PRs. So anyway, it's fun to see you here. With that, I'm going to turn things over to Stefan, and then he'll present, and then after that, I'll ask some questions, and then we'll have audience Q&A. But you can feel free to ask questions throughout. Probably we'll mix and match.
Great. Thanks for the invite, Peter. Happy to be here. I guess the title of the presentation is Hamilton. So it's a Python micro framework, and one of its uses is for tidy scalable pandas. So since this is a pandas meetup, I kind of changed language to be pandas focused, but by no means you can use Hamilton for other things other than pandas. But so Hamilton's open source, very easy to get started. Since this is a short talk, if you miss something, we have docs and examples. So hopefully, if you miss something, there's some documentation that will fill in some gaps. In terms of what is Hamilton in a single sentence, like I tried to describe it as it's a declarative data flow paradigm. So it's a paradigm meaning you kind of have to change your way of thinking and change your way of doing things. And it's a data flow paradigm, so it's describing how data and compute move together. And then it's declarative. So it's, in terms of the sense of like you're writing a transform function and you're declaring what it outputs, but then you're also declaring like what inputs are required to kind of perform that transform. So at a high level, with Hamilton, you are writing code in this Hamilton paradigm that's creating a directed acyclic graph, and then from that graph you basically ask things of it, and then Hamilton knows how to compute it. And so in which case for pandas you'd be like asking, hey, create me a pandas data frame. In terms of just so what does this paradigm look like? What's the old way of this anyway? So here I have this example of creating two columns in a pandas data frame, so C and D, where C is the sum of A and B, and D is a transform on column C. In Hamilton, you instead declare these as functions. And now, by declaring these as functions, this isn't something you can just go ahead and run. So then what I haven't shown here is some JavaScript, which I'll kind of show in a bit. But essentially, with Hamilton, the mental mapping of the paradigm is that whenever you have an assignment happening, so anything on the left-hand side of an equals, you're essentially, especially with pandas, it's when you're creating a column, that becomes the function name. So you declare that as an output. So the function name declares like what's an output you can get. And then you're using the you're then declaring as function input arguments the required kind of dependency. So what's required to compute it. So in the case of C, we're declaring, hey, look, A and B are required, and then the logic gets put into a function there. And then, so for D, to compute D, we're then declaring like, hey, since D depends on C, and in Hamilton, you write a function called D. We're declaring an input argument C, and then the body of the function does the actual logic. But that is the kind of the paradigm. A full hello world kind of looks like something like the following. So you have to write a separate file module where your Hamilton functions are defined, and then you're writing this driver code, which is actually the way that you materialize the result and get something out of it. So the purpose of the driver is to import, say, a Hamilton module or two, but then it's you're actually importing then the requisite Python modules that house your Hamilton functions. From there, you're telling Hamilton, hey, construct me this DAG object from the modules passed in. Here I'm only passing in one module, but you can pass in many. And then you're also potentially passing in maybe some configuration to help configure the DAG, or some initial data that is invariant between execute runs. And then you're telling Hamilton you can model the superset of possible transforms, and then only request a few of them, and then Hamilton will figure out how to walk the DAG and kind of compute a result. By default here, Hamilton is set up to kind of return a pandas data frame. Now there are ways to tweak this, but and so I'm not going to go into that in this talk, but just to lay that out there. So in short, the Hamilton kind of paradigm. So anywhere you had an assignment operation, you're essentially going to be writing a function for it. These functions declare a DAG or a data flow. And then from that DAG, Hamilton handles kind of walking it and kind of executing and computing a result. So just to hammer home, you're going to be writing Hamilton functions in a module, and then in a separate place, going to be writing this kind of JavaScript that connects everything together. Hamilton builds a DAG from it, and then you ask of it to be to compute something, and then it will walk the DAG and compute a result. So in terms of just backstory, why was Hamilton created? So why this paradigm in the first place? Well, at Stitch Fix, there was a team who was doing time series forecasting. Their process looked like the following. They get actuals, so signups, marketing spend. They would create a featurized data frame, use that to fit models, which would predict the future, and then business would have a forecast. The biggest problem was in creating this kind of and managing this featurized data frame, and that's what Hamilton kind of set out to solve. Why was this an issue for them? Well, in time series forecasting, it's very easy to create very wide data frames. So we're essentially, for feature engineering, you're like, to create more features, they're basically using other columns as inputs to create new features. So columns are functions of other columns. Now, over time, this grows. So for instance, in which case, this chaining can get pretty long. So if you make some updates, or, it can have adverse implications downstream, in which case, this was really causing them problems. And just to give you some grounding of what that means, so here's a caricature of what their kind of their featurization script was doing. So essentially, at the beginning, loading actuals data, and then essentially for the rest of the script, creating columns. As you can see here, it's like there's a lot of inline manipulation, maybe a function written and then delegating to a function. But I want to say, this script looks pretty manageable for the amount of features it has in it. But once you scale to over 1,000 kind of features and a growing team over a bunch of years, essentially this was causing impacting the team's ability to scale and do more, because they were tripping up over the code base. So why was that? So one, testing, the script is really hard. Where do you put unit tests if everything is in these inline, one-liners? But then integration testing is also difficult. So if you add one more thing here and you want to test things end to end, you have to compute everything to just test that one output. And then This impacted code reviews since you really have to understand the code base to kind of make sense of like, is this a good change? And then therefore this kind of impacted onboarding. It got harder over time, and then debugging was non-trivial for someone starting, since the most tenured people were the most capable in terms of debugging, just because they understood where all this where all the noodles connected when this kind of spaghetti code base. And I want to say this is generally like an underrated problem. Like most people take this as a given, or like this is the state of the world. I want to say no, it doesn't have to be. So Hamilton at Stitch Fix, it's been around in production for over 2.5 years. We only open sourced in October last year, but at Stitch Fix, it manages over 4,000 feature definitions. All features are unit testable, documentation friendly, and they're essentially stored and curated in Git. So there's like a nice kind of versioning story there, and the data science team that uses it loves it. So they had a monthly time series forecasting and featurization task that would take on the order of the day just by switching and writing features in Hamilton. Now that takes less than 2 hours, so like a 4x kind of speed up. And then subsequently, they found it's easy to onboard new team members. So enabling kind of data science rotations is now something that's possible for them, since they can get people ramped up reasonably in a shorter amount of time than before. And then they've also found that code reviews are much simpler, so reviewing code doesn't take that much time. So that was, what is Hamilton and why was it created? So just to give you a general sense of the overview of Hamilton. So one, you're going to create functions that are in separate modules. Two, then you're going to create drivers that kind of, take whatever these modules and kind of describe what you want to be computed from the DAG, and then you're going to execute this driver code. So notes, as I said at the beginning, Hamilton works for any kind of Python object creation, not just pandas. So you can use it to model fitting, or you could use NumPy directly, etc. Like Hamilton doesn't constrain you there. And then in terms of actual usage, so you could use Hamilton. It's a micro framework. You can embed it into a batch setting pretty easily. You can run it within anywhere that runs Python: Airflow, Dagster, Prefect, Flight, even a Jupyter Notebook, right? And then since it's the dependency footprint is pretty small and it's micro framework, you can also embed it and use it in an online setting. So in anywhere that you can run Python in a web service or streaming setting, you can also embed Hamilton there very easily. So in terms of, just to give an example of a walkthrough of what it's like. So say we're modeling featurization. We need to create at least 2 files if we're going to use Hamilton. So one is like it's going to encode loading data from somewhere and then featurizing it, and then you're going to be writing this kind of runpy or like a driver script that will describe what modules are required, so Hamilton can create a DAG from it, and then you're going to be asking what you want computed from that DAG. So in which case creating a pandas data frame. In terms of just to hammer home code that needs to be written again. So with Hamilton, the idea is you write functions. So you'd split things into like, here's a function that loads data. It's important then to kind of normalize column names here, because everything needs to be valid Python variable names. You need to then create a common index to join on, so that everything can merge together nicely at the end. Then you're going to be writing your feature functions. You can optionally model fitting as well. And then you're going to write these kind of driver code to materialize data for the different contexts that you want to use Hamilton in. And then again, you can model the superset of the possibilities of what you want it to be featurized. But with Hamilton, you only, by specifying only what you need, the DAG only walks is only walked to compute what you requested. So visually, you'll have some source tables. You'll write some loader functions. Those loader functions will then expose, some columns for featurization. You'll write those kind of feature transform functions, and then you're going to write, a driver that will then kind of specify what should be computed, and it will walk the DAG to only compute what you requested. And so in terms of, pandas, the problems with pandas code, I think at least at Stitch Fix, the problems we kind of saw, and I think this is feel free to, if this is spicy or you disagree, but essentially it's pretty easy to write, especially if you're writing a single script with a lot of kind of featurization. It's really easy to write highly coupled code. So meaning it's very hard to reuse what you did in different contexts, because it's really tied to like how you got data, and it's how it's organized in that single script. And then therefore this impacts the ability to potentially, reuse your work in other places very easily. Invariably, you cut and paste things, or like that is the easiest thing to do, in which case you get duplication of stuff around the place. And then, if you're spending your time trying to figure out, how to debug stuff, how you wrote it potentially, takes away from your ability to get more work done. And then obviously, if your data is too big to fit in memory, then you have issues. You have to figure out some way to like scale pandas. And similarly, how do you parallelize computation if you are doing a lot of things at once? Then that's a challenge you kind of need to figure out. Good news is Hamilton really helps on the scaling the human team size, how you organize and think about it. And then Hamilton has integrations to kind of scale, so beyond your laptop. But I'm going to skip that part for this talk since I'm trying to keep it short. So scaling the human team aspects of pandas. Well, here I have a Hamilton function. Since this is the core abstraction, here's an example one. None of you have seen this before, I want to say. So in which case I'll give you, a few seconds to kind of grok it. But I guess the point here is like, without me having to tell you what it is, I feel like this code is pretty readable and understandable. And if you were given this code to inherit, I'm pretty sure you'd actually be pretty fine, being the owner of it. Just to kind of, hammer home, some of the features of why I think that's the case. As you look in this function, I think unit testing this function is super easy. Nowhere have we leaked, how data gets to it. We just actually defined in our data, like, we've declared what inputs we require, and then what we're outputting, and then, the logic is pretty self-contained. And so in which case, unit testing these functions with Hamilton, feature functions, or any transform functions is very, very doable with Hamilton. You can see documentation. Well, there is the documentation string, a nice place to do, a great place to put documentation as to what this thing is doing. Because Hamilton forces you to get one output, the documentation relates, coupled really easily with that, with the logic of that transform function. And then because Hamilton depends on, the naming of functions and input parameters, these generally end up being something useful. So seeing in a code base foo bar is very unlikely with Hamilton, because you're forced to try to name something useful, because that is an output that you can kind of get out. And so with that, I think that leads to code being a little more self-documenting. You have the function doc, and you can also, because we build a DAG from it, we can also draw you a visualization of what execution actually will walk through. And then as in addition here, you can also tag extra metadata onto things. So it's actually very easy to, I didn't have to tell you, but you can probably see, you know who owns this function, and, there isn't any, PII information in it. Or doesn't operate over any PII information. In terms of modularity and reuse side of things, because Hamilton gets you to write these functions decoupled from context of use, right? It's it's much easier to use this function in multiple contexts. Actually, you don't even have to use a driver code to use this. Since it's in a module, you can just import it into your REPL and have at it, right? And so Hamilton really forces you, requires you to do it. And so in which case the modularity and reuse aspect of Hamilton is there from kind of day one. And then what happened at Stitch Fix is, since you kind of start to curate these functions into modules, and then if you pair it with, say, versioning and Git or publishing in Python packages, you have a pretty reasonable story for actually versioning your feature or your transform computations in a pretty sensible manner. And then you might have guessed what this check output decorator does, but Hamilton also has a very lightweight capability of adding runtime data quality checks. So hopefully, without me having to tell you, you probably understood that when this function runs, we're going to check the output, and we're going to expect a float type, the range of values between -5 and 5, and we're going to allow there shouldn't be any NaN values. So in terms of mechanically, just to hammer home the code base implications, so everything's always in modules, and then you write driver scripts that are decoupled from functions. So at Stitch Fix, you end up thematically organizing your functions. So all the spend features or transforms are together, the marketing ones together, customer ones are together, and then you write different driver scripts for different contexts. So one for your notebook, one for your actual production job, or one for running things locally, right? And so with this kind of setup, you get code reuse from day one. It's very easy to reuse other people or other teams' work, or even the work you did previously. And I want to say, because these driver scripts only contain information with respect to their context, it's really, I want to say, low maintenance burden to support them, since if something changes, they don't have any logic in here. It's very, you don't have to, migrate too much if something changes. So in short, yeah, I'm doing on time. Okay, so Hamilton, I guess, is a declarative paradigm to kind of describe data feature transformations. It's embeddable anywhere that you can run Python. It grew out of the need to tame a feature code base. So do go ahead, try it. Let me know if it helps, tidy yours. And essentially, if you thought about it, like Hamilton essentially scales the human kind of side of writing transforms by essentially making software engineering best practices something that's easy and natural. You don't need that experienced software engineer or someone with software engineering experience to tell you, hey, don't do that. Here with Hamilton, it kind of, you're forced to do it from the beginning. And then if you pair Hamilton with a system such as Modin or Array, then it's actually very, which I didn't kind of discuss or talk about here, but essentially together, Hamilton allows you to scale the compute, the code organization human side of things, and also the data compute side as well. So we'd love for you to try it if you haven't. Pip install SF Hamilton. Star us on GitHub if you like it, and then we're also more than happy to have issues created or thoughts, and then we also have a fledgling community on Slack that you can join if you have questions or thoughts. Oh, that's all I had. Thank you. Questions?
All right, great. Okay, well, I have a bunch of questions, so I'm really excited that I get to ask them first, and then other people, if you have some in the chat, I'm happy to share this as well. So I was playing around with the interactive notebook use case of Hamilton, and it seems to me that the sort of batch use case makes a lot of sense. And I was curious, what's your advice for data scientists who mostly do things in notebooks where it's like exploratory, or a high percentage of what they do is that way? Like, I feel like there's an overhead to systematizing things the Hamilton way. So maybe I would wait until I find myself like doing the same kind of thing 2 or 3 times and then Hamiltonize it. How do you think about the interact?
I mean, so that's a good question. So what we found is, so we have a few ways that you can kind of iterate in notebooks. And so essentially, like, I think you're kind of alluding to it, but Hamilton, one of the ideas we did at Stitch, so we're trying to actually reduce the development to production gap. And so, which case, by doing things in Hamilton, like, it's very likely you're pretty close to your code being production ready. But when you're in a notebook and doing exploratory stuff, you want to do things quickly. So invariably, so you can either create a separate Python file in your notebook setup, and switch back and tab back and forth between your actual kind of Jupyter notebook script and your Hamilton files functions in a particular module. There are directives with Jupyter Hub that you can set auto reloading, so you don't have to. You just have to go to your module with your defined Hamilton functions, hit reload, save it, and then Jupyter will automatically reload it. You can also, we also have a little helper module called ad hoc utils, so that if you wanted to create a module that group a bunch of functions that into a module, you can do that within your Jupyter notebook if you wanted to. So so at least the feedback we've gotten from a perspective of I have to create functions in a module, then manage it. There are only a few lines of setup, and you can make that really fast for you in your Jupyter setup. But to use the paradigm in the first place, that's a kind of a good question. I want to say the more comfortable you get with Hamilton, the more natural it is probably then to thinking what I'm doing. I think it is cumulative in that once you curate a little bit of a base of transforms, then you're incentivized to add to it when you start a new notebook. So I want to say, looking for actually experiential feedback there, but essentially, I think there are ways to make the iteration process smoother and faster. The only hurdle you need to do is when do you think in functions versus procedural and line code. But then, it's not unconceivable that we could give you a way to cut and paste your procedural code and have it like print out functions that you just put somewhere. But yeah, curious to hear thoughts if people have opinions.
I think I'll follow up on that by asking. So it sounds like you're pretty committed that the Hamilton way is like fairly universally applicable. Are there use cases where, so this is moving away from batch versus interactive, but more to use cases. So time series is kind of what it was born out of. Are there use cases where you feel like it's a slam dunk? I would guess that's like standardized feature stores and time series and things. And then are there use cases where you're like, for example, I'm thinking about, there are some times when a lot of what I'm doing is group bys, get a data frame, and then visualize it in some way, but I do it with a lot of different data frames. And I was trying to think of like how to think about the Hamilton world, Hamilton philosophy in a world where I have a lot of data frames as opposed to one beautiful one.
Yeah, so I guess there's a few things to unpack in that, I guess, in terms of what it's good for. I mean, like, it came from time series feature engineering. So I think like if you are creating, lots of columns and adding and maintaining that code base, obviously, I think you accumulate software engineering debt faster. But I want to say in a more traditional place, if you're not doing time series feature engineering, then it's really maybe the velocity of features. So once you get to a certain size of maintenance, like you'll feel the Hamilton pains. I think if you have pretty linear transforms, right? Because the Hamilton, you can actually think in data frames all the way through versus columns. I think with the check output and kind of the lineage and maybe the metadata, there's now more of a story of like, hey, if you have some very basic linear transforms now, Hamilton kind of makes sense, since now it gives you an interesting composability building block, whereas before, like, we didn't have that feature when we kind of first open source Hamilton. So in terms of fit, I think it can largely work on any data transforms, but definitely geared towards pandas and Python, and doing lots of features is definitely the sweeter spot. In terms of the questions of I guess in terms of sorry, Peter, can you refresh me? The last part of your question. So there's feature stores in there. Okay, so and then so Hamilton is, and I'll get at your question here, Doris. I guess with this is Hamilton essentially defines a featureization process. It's agnostic of where data actually ends up, and so which case we found that at least at Stitch Fix it becomes a step in their ETL process. And then from there, they push it to a feature store. So it's actually something that helps you, organize and orchestrate your featureization process. Now, with Hamilton, you can have multiple sources of input. See, if you're doing pandas work, the way that things work, you really have to have the series, the indexes match up so that things will line up. Because that's kind of, Hamilton naively at the end kind of just uses the index to join things on. You can customize it, and we have hooks to do that. It's just a matter of you writing some more code and kind of adapting what Hamilton kind of does. In terms of, okay, there was one more question. What did I miss, Peter? I guess you were.
I think that's great. Yeah. So I love the idea of using Hamilton to create feature stores, and feature stores in general are super useful. If you have 1,000 columns, did you find that in practice it was like 400 functions? What do you do when you start having so many functions across so many scripts or across so many modules that it actually becomes hard not to duplicate existing functions? Like, is there a future in which I could imagine something that would like traverse and be like, hey, just so you know, there's a function that's exactly like very similar to the one you just made already, or something like that?
So yeah, I mean, like, I guess so right now this is where hopefully the naming, if you're forced to name things in a reasonable thing, the first thing you'd do is search the code base for like, hey, is something named like that? In which case with Hamilton, like the mapping of and actually Hamilton also tries to force an immutable kind of computational paradigm. So there's your output that you can get ideally, so it maps to a particular function, right? So it's very easy to map logic, see an output and map to where it was computed. And then because of the naming, how things stitch together, hopefully, like, you know, you train yourself to look in the code base first before doing that. So that's more of a human process thing. But otherwise, you know, if you import two different modules that are named the same thing, Hamilton will go, hey, you've got two things that are named the same. We, you know, stop there. So so in terms of, yeah, there isn't anything specific in Hamilton other than like hopefully the naming and the module curation. So if you're doing marketing spend features, you're looking in the marketing spend features module, and you know that's where you're adding the marketing spend. Since you know, in a traditional way, when you're adding features and you're adding those functions, most people are just appending to a script or arbitrarily, you know, inserting it somewhere within the logic makes sense. With Hamilton, it's much simpler, since the modules of things are what encapsulates, you know, the functions. Like that is really kind of the unit of curation. And so you can be, you know, from day one, Hamilton forces you to think like that. Obviously, you can have a single giant script which has everything in it, but then, you know, invariably, like if there are thematic themes between it, then, you know, they will be broken up and out into their own modules. Why Hamilton, you know, like in terms of why that team can manage so many of those functions, is because they end up being super simple, right? The naming makes sense. And then Hamilton also has in time series forecasting, there's like, you know, you get one column and you're perturbing it slightly. So we actually have like some syntactic sugar to kind of reduce the amount of functions you need to. So the function logic is only in one place. We just at DAG creation time, you know, explode the amount of kind of nodes because they're parameterized type thing. So Hamilton helps, yeah, like with some of that, I think. But otherwise, in terms of, yeah, hopefully you have a reasonable naming scheme to help you curate your functions so that you look there first.
Okay, that's great. Yeah, that makes sense to me. So this is a human question for a second, but like reading between the lines on LinkedIn, it looks like in June you finished at Stitch Fix. And is that because you're working on Hamilton full time, or, and if so, like, I'm curious, what aspect of Hamilton is what gets you like so excited to invest this much time and effort into it?
Yeah, it's a fair question. I mean, I think so at Stitch Fix, I was on a platform team, which essentially was, you know, engineering for data science. So I was trying to help, 100+ data scientists do their job better, or by providing tooling abstractions that, you know, reduce the kind of the software engineering need for them to kind of do things, I guess, to glue things together themselves, in which case they could just rely on the software engineering Lego bricks that we provided. I think since we open sourced Hamilton in October, it's been kind of, you know, interesting to see people adopt it. And then, well, with open source now, you know, my potential, you know, amount of people I'm helping is far greater than 100. It's anyone who finds a fit for the tool. And so in which case, you know, I'm energized a bit to help more people make not a mess of their code base, since I do think that is something that, you know, over time, it kind of happens, in which case, you know, Hamilton is probably a good tool there. And then since I did computer science, you know, modeling things as a DAG, and then everything being its functions also has some interesting properties, right? So it's very easy to wrap a function with certain concerns, or to add or inject things at DAG execution and walk time. So I'm kind of, you know, this got me excited also from a technical perspective as to like, well, what can we add to do this? So with Hamilton, you kind of get this computational lineage graph for free. You don't have to, you know, add that or any emit it or manually emit it or add it to the step of your job. Like with Hamilton, you kind of get it for free. So like maybe we can emit that to some governance place or some place of interest. Maybe with tagging, you can, you know, we tag data inputs with particular, you know, data access policies, and then in the driver, you know, actually check that like, hey, you're requesting this input, maybe you should, you know, are you authorized to do so, or at least like, is this machine learning use case, you know, a responsible use for this data input type thing. So I think, you know, that's obviously non-trivial stuff, but that's where kind of my mind goes as to like, what are the actual other things that you could layer on top of Hamilton, since everything's a DAG and everything's a function. So but yeah, in short, like that's kind of roughly where I'm spending my time.
Yeah, that's cool. Okay, well, I'm going to turn it over to the group for questions if there are any. I have one or two more, and then we can close after that. But if there are any questions, feel free. You can ask them in the chat. You can also come off of mute if you're brave. So while people are typing or thinking, what are you most excited about in the coming year for Hamilton?
I think Hamilton's an interesting tool to have in your toolbox if you're doing any machine learning or feature engineering. So I think, evangelization just to see like how where I could get Hamilton is, like I think anyone who's doing any machine learning should know of Hamilton to know that it's something that they could use for a particular context that helps them with organize their kind of transforms. So I think I'm interested with that, and we have a bunch of conference talks lined up about it, so excited to kind of see there. So in particular trying to get in seeing what the PyData kind of conference reaction is to Hamilton, since I do think it's unopinionated in terms of what Python ecosystem or frameworks underneath, but it does help solve something that I think is pretty broad based. So I'm kind of interested to see just seeing what people try to apply Hamilton to. So we actually had someone come in and ask for async support, since they had an async web service. And they wanted to be able to run a Hamilton graph and do some async IO with it. And so, which case it's kind of like, I never thought of that use case necessarily, but like that's an interesting one. And so, kind of interested to see how people kick the tires at Hamilton and where it goes, because I think I probably, it's hard for me to predict what use cases Hamilton will have in a year. I mean, I want to say core feature engineering and time series will be there, but really, like, to what extent will people be using Hamilton for other means is kind of up in the air for me. But
I have one more question, and then we can close. So at first, when I heard about Hamilton, I thought that it would play really well with Great Expectations. It's interesting. Today, I hadn't known actually that you could build kind of an expectation-like concept into Hamilton itself. So that makes me think they're more competitors than I previously thought. How do you see things like, can Hamilton coexist in a Great Expectations stack? If so, how does that work?
Yeah, I mean, so this is like where it gets me excited about everything being functions, right? Since then it's just a matter of, say, creating the right decorator to annotate a function with, like, hey, something that we want to happen with respect to computation. And so with the check output decorator, like we integrate with Pandera. So we have like some basic built-in checks, but we actually support Pandera. And so which case because everything's functions and we have this check output decorator, it's just a matter of potentially writing a new one that potentially could be plugging in with Great Expectations, or providing a way that Great Expectations can kind of plug into the nomenclature of how people describe things with Hamilton. So I think like with Great Expectations, to me, it's a system that stores state. You can go back and look at previous runs. You can kind of augment tests. I think with Hamilton, the difference in philosophy is that we want everything to be as close as possible to the code and the transform. And so which case I could see an integration where maybe you have some named ID to use Great Expectations, and then at runtime we connect to some Great Expectations system that then knows what to compute to store a result, or maybe that's where results are logged. So I do think like Hamilton can play nicely with it. And then actually from a platform teams perspective, like my ideal is like, how can you define this kind of expectation decorator in a way that you could change from Great Expectations to, I don't know, DQ or to YLabs or something without having to do massive surgery on your code base, since everything's limited or like contained to that single decorator. So I think there's some interesting ways that we could approach this problem. And I think to me, really the question is about like, what is the user experience we want, and then who's going to be managing it? And so how can we build an experience where it's easy to manage and plug in such a platform as Great Expectations, but then the user really I want to assume that most data scientists probably don't care whether it's Great Expectations or something that Hamilton does or YLabs. They just want to know whether things are broken or not. And so I think I think there's some interesting building blocks that Hamilton enables that to play around with that experience.
Yeah, great. Thank you. Thank you very much. Elijah had a comment chat. Actually, do you want to come off mute, Elijah, and just you can say that.
I was just thinking when Stefan answered like, why is he doing Hamilton full time? Like, oh, why am I doing this? I'm like, both as part of my job and kind of like nights and weekends. To me, it like solves a problem of how to build a computational workflow in a very novel way. So the Hamilton core abstraction couples the like transformations you make with the structure of their dependencies, which is like, oh, why would you couple it initially? But then when you think about readability and maintainability, it starts making a lot of sense. So starting from that as a first principle, I find that to be like a really natural way to build and understand these pipelines. And I kind of want to like stick this hypothesis into the industry and churn it a bit and see like whether other people agree. And so far we've gotten a bunch of really good reception. So there's a possibility to change the way that people think about these transformations in a really cool way. So that's why I'm excited.
Yeah, that's great. That's great. Well, I have many more questions, but we should close for time reasons. But thank you so much, Stefan and Elijah. It's great to hear from you as well. And thank you for the work you're doing in Hamilton. It's really exciting. Yeah, we appreciate your being here today.
Thanks for having me. It was good fun. Yeah, if anyone has questions, yeah, feel free to find us in the Slack channel or Twitter or LinkedIn.